All right, physicists, welcome to our Unit 1 review. In this video, we're going to try to go over the various material that you're going to need to be successful on Friday's test. Okay, so what does this include? This includes electrical forces, electrical fields, electrical potentials. And this is the formula sheet that I will be giving you on Friday. Notice that these are just constants that you may or may not have reason to use. You're going to need to know a little bit about dot products. You're going to need to know a little bit about trig functions, not much. And then most of it is going to be in Coulomb's law, electric field from a point charge, forces from electric fields from some more exotic charge distributions, so like a line of charge, dipole, sheet of charge, and then the potential energy from a group of charges, electrical potential, and then calculating the electrical field from the electrical potential. Okay, so what's our first topic? Our first topic is forces and charges. Now remember, we have two types of electrical charge, positive and negative, and charges move around easily in conductors, not so easily in insulators. The amount of charge that you have in total is conserved, so you can start out with an object that has zero charge. You can take some charge off, and that'll leave the original object, if you take a positive charge off, you take away some nuclear centers, then in that case, you would leave a negative charge on the other. Okay, so if one gets a negative charge, the other would get a positive charge. If one gets a positive charge, the other one would be left with the negative charge if they both started out neutral. And we talked about how objects can be charged by conduction. That's where you start out with an object that's charged, you have another one that's uncharged, you touch them together. After you separate, they both are charged. Induction, that was where we had one charged object. So you bring an uncharged object, it gets polarized. That means that the charge separates within the object, and then you can touch it and ground it to take some of the charge off. In that case, you'd end up with a positive charge and a negative charge, or a negative charge and a positive charge, opposite charges, whereas if conduction, we usually would end up with the same type of charge. And I think it's okay to think about polarization as just a different type of charging where the charge is shifted around within a single object. Now the forces that arise from these, at the moment we're just going to think about them as arising from static charges. So Coulomb's law tells us if you have two objects that are not moving very fast or are standing still, the force between them is just dependent on the two charges of the object and how far apart they are from one another. And then this number out in front is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. Now notice on your formula sheet, I have only given you epsilon naught. So if you want this number in your back pocket, you can always memorize it, but the number that you're going to get is slightly less useful 8.854 times 10 to the minus 12. And this is usually given farads per meter, but I think it's okay for us to think about this in Coulomb squared over Newton meters squared. And what are the units on this doing? The units on this are making sure that both sides of this have units of force. Force is in newtons. This is in coulombs squared because it's coulombs times coulombs. This is meters squared. So this whole thing has to have units of newtons times meters squared over coulombs squared. Cancels out the coulombs, cancels out the meters squared. Leaves us with something that's a unit of force, which is newtons. All right, now I have given you on Canvas a review sheet that very closely mirrors what you're going to see on the test. So a good strategy for doing well on this test is A, spend a lot of time making sure you understand every formula on the formula sheet, and B, make sure that you understand every question on the review sheet. So here's a tricky one, deceptively tricky. It says a positively charged insulating rod, okay, plus, 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 is brought close to an object that is suspended by a string. If the object is attracted to the rod, okay, so presumably by Newton's third law, they're going to be attracted to each other. It's hanging on a string, it gets pulled towards. Can we conclude the object is positively charged, the object is negatively charged, the object is a negative insulator, the object is a conductor? Well, I think we can rule out that the object is positively charged because in that case, they would be repelled, not attracted. Negatively charged, possible. Object is an insulator or conductor. Again, possible, but you can't conclude any one of those things just from the fact that they're attracted to one another. The one that I want to point out to you, the object is negatively charged. That one's a little bit tricky because if this has an overall zero charge, the object could still be polarized such that there's more negative charge on one side and more positive charge on the other. In that case, this would still experience a slight attraction to the rod. So in fact, the answer to this one is none of the above. I say this one's tricky, but I have not put a question like this on the exam. I just want you to be aware that this is things can be complicated, right? Anything with electricity, there's always a degree of thinking that is required. Okay, so here's a more straightforward question that I would expect you to understand. It says the diagram shows two pairs of highly charged cubes 1 and cubes 2 and 2 attract each other, and cube 1 and 3 repel each other. Okay, so let's just for fun, it doesn't tell us which type of charge we have on either one, but let's pretend this is a plus. That would make 2 a minus. And then if this was a plus, then these repel each other, so this would have to be a plus. Okay, so this is more the type of problem that I would put on the exam. It says, which of the following illustrates the forces of cube 2 and 3 on 3 and 3 on 2? Well, because of this relationship, we can tell positively that 2 and 3 have opposite charges from one another. So 2 and 3 would pull on each other. And there we go. The opposite, we have our Newton's third law type of pair right there. Of course, we could also, in this case, say what type of force would we expect if cube 3 was neutral, for instance. If cube 3 is neutral, has zero charge on it, then in that case, you wouldn't get that either attractive or repulsive force. Okay, and that goes along with this Coulomb's law. Okay, so you can only get a charge if both, or a force, if you have some charge separation or some net charge on both objects. If one of them has a zero charge, then you won't get any force. So this is a kind of straightforward problem, but you should expect to see something like this. Two identical charges, 2 meters apart. Okay, R equals 2.0 meters. Meters is the good units for this. Exert forces of 4.0 newtons. Okay, there's your F. On each other. The value of either charge is. So this type of problem, I can give you lots of different versions. I could, give you a charge, a distance, and a force, and ask you to find the other charge. I could give you both charges and a distance and ask you to find the force. I could, So all of these are things that you can switch around. The only thing that's a constant is this. This part is the constant measured in the lab as around 9 times 10 to the 9th. And if you want to, in this case, it says both charges are identical. So instead of having Q1 and Q2, it would just be Q times Q or Q squared. So in our case, it would be F equals K Q squared over R squared. It asks you to find each charge. So I can go ahead and rearrange this and get Q squared equals F R squared over K, or Q equals square root of F R squared over K. And at that point, it's your job just to stick in the numbers, force in newtons, R in meters, and then K in Newton meter squared over Coulomb squared. And this will end up having units of coulombs. Okay, so any type of problem like that is fair game. Another type of problem that's fair game is adding up forces. So let me show you what I mean by this. It says 2 electrons, E1 and E2, and a proton, P, lie on a straight line as shown. The directions of the force, E2 on E1, the force of P on E1, and the total force on E1, respectively, are. Okay, so in this type of problem, the important thing to identify is what has positive and negative charge. So this is an electron. It has a minus E. Remember, E is that fundamental charge of 1.6 times some other stuff times 10 to the minus 19th coulombs. That number will be given to you on your formula sheet. So there's a minus E, here's a minus E, here's a plus E. Now we're looking for forces acting on E1. E2 is closer to E1 than P is. So because they have the same amount, the same magnitude of charge, you can tell that the contribution to the total force is going to be bigger from the one that's closer. This is because our Coulomb's law says that F equals K Q1 Q2 over R squared. That 1 over R squared dependence of the force says that things that are closer have a bigger force. So the force on E1 of E2, since these are both negative, they repel. So there's your force from E2. And then it's going to be, the E1 is going to be attracted towards P. Okay, but I've drawn this as a smaller arrow because it's the proton is farther away, so this force is smaller. And now if we add them like vectors, we have a vector this way and a vector that way, but this vector is smaller, and so the net force is like that. So it says the directions of the force of E2 on E1 is this way. The force of P on E1 would be that way. And the total force would be this way. So left, right, left. Let's see if we got one. Left, right. There we go. Okay, so I feel confident saying that you will see a problem like this on your test. And just to make sure that you understand, I'm giving you questions that are like the questions on your test. They are not the questions on your test. So if you don't understand this question, you're going to get the question on the test wrong. So I'm trying to be your friend a little bit, but I'm also kind of your adversary. So take this review seriously. Okay, so we did forces. Now let's think about electric fields and fluxes. Well, our second step in this unit was to think that forces are caused by an electric field when your particle, your charge is sitting inside. So if I have a charged particle, I put it inside an electric field, it feels a force. So this force is in newtons, charge is in coulombs. Units on electric field have to be newtons per coulomb. Now, of course, how much the particle accelerates as a result of that force also depends on its mass. So once you find that force, you have to add up all the forces. It could be gravitational plus your electric force. The forces still add like vectors, and then you find your acceleration, which in turn is also a vector. Then in chapter 23, we also learned how to use Gauss's law to give us the electric field for a couple of symmetric geometries, for a line of charge and a sheet of charge. We also could find that by adding up vectors, but Gauss's law made it a little bit easier. And Gauss's law also said that there was a intimate connection between the flux, which, remember, because it's this dot product, it has to do with the magnitude of E, the magnitude of the area vector coming out perpendicular from the surface, times the cosine of the angle between that E vector and the A vector. Okay, so let's do a little bit of practice with each of these ideas. So here we go. An isolated charge point particle produces an electric field with a magnitude E at a point 2 meters away. So E equals K, whoops, I should have put the E, that's the one that doesn't have this. E equals KQ over R squared. Okay, so in this case, this point particle with some charge Q at R equals at KQ over 2 squared gives us that E. Now, so this equals KQ over 4 meters squared. Okay, so in a sense, we could write 4 meters squared E equals KQ. Now it asks us, at a point 1 meter from the particle, the magnitude of the field is. Well, it would be KQ over this E prime, this new electric field, 1 meter from the particle would be KQ times 1 meter squared. Okay, well, that would be KQ over 1 meter squared. Okay, not too exciting there. 1 squared meter squared. And then, because I know the size of KQ, I could write this as 4 meters squared E over 1 meter squared. And it's going to be 4 E. Okay, done. Now, those of you who took my Physics 1 course last semester know I like this type of problem. I like the proportionality problems where you change one variable between two situations where everything else stays the same, and then you you try to see what happens. And I know that this type of problem is not easy, but please know I do give partial credit. So if you wrote down this equation, I would give you probably half credit, because I want you just to show that I know what is relevant to this problem. All right, so here's another one where the questions are, what's relevant? Well, remember that electric fields tell us the direction that a positive charge would get pulled, okay, because the force is Q times E. If we had a negative charge, the force would be in the opposite direction, so the sign on this Q in this equation actually matters. Now here we say the diagram shows two identical particles, each with a positive charge q. The electric field at point P on the perpendicular bisector of the line joining them is. Well, let's call this particle 1 and particle 2. Each one of these is going to contribute to the electric field at point P. Electric field contributions point out of positive charges and in towards negative charges. So particle 1 is a positive charge. So the electric field contribution from it is going to point out. Okay, so there's my E1 contribution. Similarly, identical particle, and the electric field is going to point out of it. Okay, so these are, I'm trying to draw these as identical magnitude vectors, but they're in different directions. So there's my E1 and my E2. And if I add those together, actually let me make them shorter just so my picture's a little nicer. So there's my E1 and my E2. And if I add them together, you add them tip to tail, so it would be like this. So there's your E2, E1, and here I'm bringing my E2 over, sliding it down here. We add vectors, tip of the last one to the tail of the next. So there's my E2. And this vector here would be my E1 plus E2. Okay, so I found out what the direction of that final vector is. Okay, so in a problem like this, how would you do it? Draw in the vector for the first one, draw in the vector from the second one, do a vector sum. So like here, I know that the force in the y direction from, or the electric field component from E2 is opposite the direction of the electric field component in E1 in the y direction, and so it turns out that the entire net electric field is in the x direction. Okay, there are other things that I've asked you to learn. I've asked you to learn about the electric field from various charge configurations. One of the most important of these is the electric field from a dipole. So that's two charges that have of the same magnitude that are close to each other, and so the net charge on the dipole is 0 because you have a plus and minus charge with the same magnitude, and they're separated by some distance d. Ah, instant coffee, delicious. Okay, so if we have this electric dipole, we have for this some dipole moment. Okay, so here's our x equals 0, and it tells us that I've got a minus charge and a plus charge. My q is equal to 2.5 microcoulombs, so that's 2.5 times 10 to the minus 6 coulombs, separated by 1.0 times 10 to the minus 4 meters. Okay, so the d would be, that's the distance between these two, would be 1.0 times 10 to the minus 4 meters. Okay, so you can take the product of those two and you'll find the p, which is a vector that points in the direction from minus q to plus q, but the magnitude of that is going to be just q times d. So it's going to be 2.5 times 10 to the minus 10th coulomb meters. That's just me multiplying those two together. Now next it asks, if the dipole is oriented along the x-axis, what is the electric field at x equals 15 centimeters? So the thing to realize is that this equation is for going on axis. So if I want to use this equation, all I would need to use is z equals, I would need to go centimeters into meters, so 0.15 meters. Okay, so now you have your P, you have your Z. You can go look up your epsilon naught as, 8.854 times 10 to the minus 12 coulombs squared over Newton meters squared. And you can just plug your numbers into your equation and see which one of these you get. A little more challenging here is the Electra is another one of the type of problems, as I've said, that I like. It says charge is distributed uniformly along a long straight wire. The electric field 2 centimeters from the wire is 20 newtons per coulomb. Okay, so here's my long wire. If I'm 2 centimeters away, the electric field is 20 newtons per coulomb. If I'm 4 centimeters away, then I would have presumably a smaller electric field, but how big? Well, the way to do this problem is to realize that the electric field is proportional to 1 over r. So the electric field equals a bunch of stuff, let's call that some constant, over 2 centimeters. Okay, and so if you want to find out what that constant is, it would just be 20 newtons per coulomb times 2 centimeters. That would be that C. Now we could use that same C because that charge and that epsilon naught is all going to be the same. So here, there's our E at 2. What would our E at 4 be? Well, it would just be, again, our C over our new distance in centimeters. So here would be C over 4 centimeters. So it would be 20 newtons per coulomb times 2 centimeters over 4 centimeters. Okay, so 2 over 4 is just 1 over 2, and so this would give me 10 newtons per coulomb. Okay, so these types of problems I know are tricky for people, but it's all about looking at the equation, trying to figure out how things are changing. And as I say, half of the points on the test are just letting me know that you know what's going on. So, for instance, if I had told you charge is distributed uniformly along on a sheet of charge, the electric field 2 centimeters from the sheet is 20 newtons per coulomb. Then it asked you the electric field 4 centimeters from the sheet is. Well, notice that the electric field from the sheet of charge doesn't depend on space. It doesn't die off with distance the way that the electric field from a line of charge was. So if we had had a sheet of charge in this problem, the electric field would just be 20 newtons per coulomb still. So it depends on what type of object is producing the field. Okay, so that's what you need to be aware of in this sort of problem. Okay, now what will a short answer question with this sort of material look like? Well, the hard part about electric fields is that you do need to consider them as vectors. Okay, so how would I do this? Well, it says, I'm going to sketch this problem. It says a positive charge with Q1 equals 1.2 times 10 to the 5th is located on the x-axis at 2 meters. Okay, so there I am. There's my Q1. and it has a plus charge. A negative charge with Q2, which is a negative charge, is on the y-axis. It's a minus charge. Q2. Now, part A asks, find the electric field at the origin in vector component form with correct units. Well, this is going to have a contribution from my Q2 and a contribution from my Q1. Now, the thing to realize is that the contributions from a positive charge are going to be pointing out. The contributions from our negative charge are going to be pointing in. So it was necessary for me to draw this and to identify, do I have a positive or a negative charge? My E2 is going to be pointing in like this. My E1 is going to be pointing, whoops, no, I'm right, pointing out away from it. So there's my E1. And so in this particular case, right, it's not universal, but I drew it this way. I would have to find my E2, my E1, and my E2 by plugging in the numbers, getting a KQ1 over R1 squared. And I'd have to find my E2 equals KQ2 over R2 squared. R1 and R2 just being, here's my R1, there's my R2. And then my total electric field would be, my E1 is going to be in the minus X direction, so it'd be minus E1 times I. And then my E2 is in the plus Y direction, so it'd be plus E2 times J. Okay, and the units on this, if I put all the numbers in correct units, would be newtons per coulomb. The next part asks, find the magnitude of the total electrostatic force on the electron positioned at the origin if it is acted on by the electric field resulting from the presence of Q1 and Q2 as described above. Okay, well, the F, if I'm just taking the absolute value, it just is asking for the magnitude, it will be just the magnitude of the charge, which in this case would be E times the magnitude of E. So that in this case would be, you know, your 1.602 times 10 to the minus 19th coulombs times, and if I want to find the magnitude of this vector, the vector is ultimately going to be pointing in this direction, right? Because it has an X component and a Y component. And so if you wanted to find the magnitude, you'd have to use Pythagorean theorem. So it'd be E1 squared plus E2 squared. Okay, so there's nothing that's just trying to trick you in this problem. It's all straightforward, but I know that when I had a problem similar to this on the test last year, people really freaked out and did not do very well. So that's why I'm trying to step through a little bit more carefully this time. All right, now a topic that we used a little bit in this unit was Gauss's Law. This helped us do some calculations to figure out in an easy way the electric field around an infinite line of charge and around a infinite sheet of charge. So let's take a look at, here's a Gauss's Law type of problem. It says a particle with a charge of 5 microcoulombs. So you should, whenever you see something like this, you should always be converting it. 5.0 times 10 to the minus 6 coulombs is placed at the corner of the cube. The total electric flux through all sides of the cube is. Well, here's how I've given you Gauss's Law on your exam. If you want to find flux, of course, it is the electric field dotted with the dA, but you also want to have that connected to the enclosed charge. So if we know what the enclosed charge is, we can pretty easily find out what our flux through the cube is just by taking the flux equals Q enclosed divided by epsilon naught. Okay, so in this case it would just be my 5.0 times 10 to the minus 6 coulombs over 8.854 times 10 to the minus 12. And on the sheet I've given it in the traditional units of farads per meter, but we know that this is coulomb squared over Newton meters squared. And you can go ahead and plug those numbers in and find what that is. Now, here's a tricky problem. And I'm thinking I might put a problem like this on the test. So I thought I'd walk you through the logic. No part of this is hard. And I think it's fair because we did this problem in lab. So let's make sure we understand it. It says we've got a Gaussian cube below. Okay, so this is what it looks like. You've got a bigger electric field on one side than on the other one. Okay, so we have, let's call that the E in the left and E on the right. And I give you the sizes of those. And they give you the size of each edge, which is 0.1 meters. And now it asks, what is the electric flux through the left and the right faces of the cubes? Give the an answer with the correct signs and with the correct units. Okay, so I have given the length and width. So this is going to be 0.1 meters, 0.1 meters, 0.1 meters. And so I've also given you the size of the electric field, 6 times 10 to the third, 4 times 10 to the third. So finding the flux through the left and the right side should be fairly straightforward. The area vector over here points out such that the angle between the area vector and the electric field vector is 0. The area vector on the other side points out the other way. So the angle on the other side would be 180 because the area vector and the electric field vector are pointing opposite directions. So if you wanted to find the flux on the left side, it would be the E times the A times the cosine of the angle. Okay, so this would be 6 times 10 to the third newtons per coulomb times, and to find the area it would be 0.1 times 0.1, so it would be 0.1 meters squared, so that would be 0.01 meters squared, and then you'd have cosine of 180. So this would be a minus 1. Okay, and then on the right it would be the same thing. It would be E times A times cosine of angle, so that would just be 4 times 10 to the third newtons per coulomb times 0.01 meters squared times cosine of 0, which is just 1. So on the left you get a negative flux, on the right you get a positive flux. Now, so that's part A. Now part B asks, using Gauss's law, how much charge is enclosed in this box? Well, if you want to find the charge now, the Q enclosed is just going to be epsilon naught times the total flux. Now, because the flux is pointing just in the, the x direction here, and our area vectors for the top and the sides would be in the y and z directions. Those angles are 90 degrees essentially, and so those do not contribute to the flux. So the total flux of our box would just be the flux from the left and the flux from the right. That would give you a negative number because this left is a negative flux, this right is a positive flux. And then if you wanted to find the charge inside, it would just be this flux times epsilon naught. Okay, so this epsilon naught is a number all right. So here's your A. Here is B. B, you time the total flux. Your enclosed charge in the example I've given you here should be negative because the negative contribution on the left is bigger than the contribution on the right. Positive contribution on the right. Now C is a little bit badly worded. I'll want to rewrite the sentence a little bit before the test, but it's essentially okay. It says, if this charge is arranged uniformly on a single thin sheet, what is its surface charge density, sigma? So the idea here is that I'm having you imagine, what if all of that charge is arranged like this? And essentially, in this, I'm just asking you to tell me what is sigma. Well, sigma is the charge per unit area. So if I took that total Q enclosed divided by the 0.01 meters squared, that would give me a number that has units of coulombs per meters squared. Whoops. 0.001 meters squared. We don't have to square that again. All right, now this last part, I admit, is the trickiest part. It says this electric field is caused by the vector sum of two contributions, one from the uniform thin sheet of charge and the other from an external field that is constant in space. What is the external field's magnitude? Is it pointing to the right or to the left? Well, let's see how this works. Now, we established already in part C that this is going to be a negative charge. It's because we found a negative enclosed charge. And so the electric field contribution from this is going to be pointing towards. On the other hand, my electric field in this picture, I have bigger over here and smaller over there. So if I am putting this whole thing in an external electric field, I would need that external electric field to be pointing this direction. So here's my external. And then my internal electric field is from this extra charge that's in the box. And so since these are adding together, my E external plus E internal is going to equal 6 times 10 to the third newtons per coulomb. And then my E internal is going to be, the E external is still in the plus X direction, minus my E internal in the is in the positive direction, 4 times 10 to the third newtons per coulomb. Okay, this is a system of equations you can solve very easily. You can just add these two together and you get that 2 times E external equals 10 times 10 to the third newtons per coulomb. So ultimately E external is equal to 5 times 10 to the third newtons per coulomb in the I hat direction. Okay, so there's a lot of physics in this problem, and I think it's more of a fair question because we've gone over it. So I want you to try to think this one through. It's a good problem. Okay, now finally, in the last week, we've been doing electrical potentials and electrical potential energies. And the idea here is that we have the potential energy as we say, what if we consider that as zero with the particles infinitely dispersed? And then we can try to calculate the energy when you bring the particles in and set them up in relation to each other. So we figured out how to add up the energies of pairs of particles. Then we introduced the idea of the electrical potential. So energy is in joules. Now the electrical potential has units of joules per coulomb, and it says, what if you put a charge, units of coulomb, into this potential, what kind of energy would it have? So U has units of joules, volts is a unit of joules per coulomb, and so it's telling you about the energy per unit charge extra that you put into that potential. Now the electrical potential and the electrical field are intimately related because essentially the electrical field is negative the slope of the potential. So, okay, here's a sort of short answer question. It says 3 protons initially separated from far distances are brought together to sit in a straight line with each proton 2 times 10 to the minus 6 meters from the next. Okay, so this is D, this is D. Let's call these 1, 2, and 3. Each one has a charge of E, E, and E. So if you have 3 charges and you want to add up the total energy, you just need to consider all the pairs. So my total electric energy would just be U12 plus U1 and 3 plus U of 2 and 3. Okay, so in this case, my energy is K Q1 Q2 over R, not R squared. So let's bring out the K. Q1 Q2 is just going to be E squared for all of these. And then for my U12, it would be 1 over D. So this is my first term. Plus U13 would be 1 over 2D. And then U23, 2 and 3 are only D apart, so that would be 1 over D again. Okay, so here I can again go K times that charge, because I only can say this because they all have the same charge. So if this was 2D over 2 over 2D, 2 over 2D, 2 plus 3 plus 1 is 3, plus 2 is 5, so it would be 5 K E squared over 2D, and then you can just stick in your numbers, okay, because you know that your K, that's 1 over 4 pi epsilon naught, it's 8.99 times 10 to the 9th Newton meters squared over Coulomb squared. Your D is given to you as 2 times 10 to the minus 6 meters, and your E in this case would be 1.602 times 10 to the minus 19th coulombs. Okay, so if you want to find the total energy, you just have to consider all of the pairs of particles within a system. Now, an easier type of question is how would you find the changing potential energy? And it says, if 500 joules of work are required to carry a 40 coulomb charge. Okay, so the work is the amount of, it's the amount of change in potential, or change in energy is going to be 500 joules. And it says, if that much work is required to carry a 40 coulomb charge, so Q equals 40 coulombs, the potential difference between these points is. Okay, so they're asking you in this question, what's the potential difference? And so delta V equals delta U over Q. Okay, so that's your 500 joules over 40 coulombs. Okay, so you'd have 12.5 joules per coulomb, or volts. And finally, what is the relationship between the potential and the field? This is what we're probing this week in lab. The relationship might not be totally clear. This is the equation that I'm going to give you on your test sheet, but it's going to be easier in this finite version of it to just write minus change in V over change in X. And if you're just looking for the magnitude, you don't have to worry about that minus sign. So that you could say this. Now it asks, a geologist measures the Earth's electric field near the surface and finds that the equipotential lines 100 volts apart, so delta V equals 100 volts, are at a distance of 75 centimeters from each other. So delta X equals 0.75 meters. Assuming the electric field is uniform, what is its magnitude? Well, if you want to find the magnitude of E, then I can take the magnitude of V over the change in V over the change in distance. So 100 volts over 3/4 meters. So I would have 400 divided by 3, and so I would get something around 130 volts per meter. Okay, so I know it's kind of a lot, but the ideas are not that many. You've got to have your forces adding like vectors, electric fields adding like vectors, a little bit of Gauss's law, and then finally a little bit about electrical potential energy and electrical potential. There are going to be 10 multiple choice questions. There's going to be 5 true and false questions, and the short answers are going to be very similar to the ones that we reviewed today. So good luck studying. If you have questions, feel free to come see me at office hours or to shoot me an email.